what we finished with yesterday is how PCM works. You have some analog data and you want to convert it to digital data and then send that digital data. And what we do is we take samples of the analog input. And for each sample, we measure a value. So we have a sampler, we measure the value and map it to a code number or a level. So the two parameters which are important are the number of samples per second is one parameter. How many samples do we make in some period of time? And the other one is the number of code numbers or levels. Where the code numbers is the value that's obtained after taking that sample, the discrete value. The question is, what are good values for these, for sampling, for pulse code modulation and other codecs? We know that the more samples we have and the more levels or code numbers we use, the higher the quality of the reproduction. That is, we'll get closer. If you remember to yesterday, we had those three cases and we had the original input, the blue line. As we increase the sample rate and we increase the number of code levels, the output becomes closer to the input. That is, the quality increases. Make these higher, the quality goes up. How big is a CD in terms of data? How many megabytes can you store in a CD?
700.
All right, about 700 megabytes. Normal CD, you burn data to about 700 megabytes. What about an audio CD? You know those things, not MP3 CDs, but a real audio CD. Anyone purchased one recently? Audio CD? A CD with music on it? Have you bought one recently? Yes? How many minutes of music were on it? About. How many songs?
10.
About 10. How many? 200. You've got an MP3 CD. That's not fair. I mean original audio CD, not with MP3 but with high quality CD audio. Maybe 10 songs, 15 songs. About how many minutes do you think in total? 80, maybe 1 hour, between 1 hour and 80 minutes. So why? Well, with audio, music, for example, what we do, the music that we record on that CD, the music is the analog input, but we need to convert it to bits, to digital, to store on the CD, because we store it as digital data on the CD, some bits. This is the total number of bytes that we can store. So the question then is, how much music or how many minutes of music can we store? It turns out that not MP3 CDs, but audio CDs use PCM, pulse code modulation. Music typically ranges in frequencies from the low frequencies, several hundred hertz, up to approximately where? What's the spectrum of music? Look in your slides. There's in one of the first lectures, there was a slide that showed the spectrum for voice, for music, and for other types of data. Anyone remember? Almost at the start of the lectures. I can't remember. One of the first lectures, we have a plot which gave the spectrum of data. Where was it? Yeah, that's getting close. It was on page 24 of your handouts. At the bottom, there was a plot that showed speech and music on page 24. And you see music, the frequency ranges up to about... So music ranges in frequencies of about 100 hertz up to about, let's say, around 20,000 hertz. Music is spread across a range of frequencies. The maximum frequencies of most music are around 20,000 hertz on page 24 of your handouts. So, the question is, if we want to convert this analog data, this music, into digital, we can use PCM. But the two parameters we need to consider are how many samples per second and how many code numbers. So how often do we sample the music? And when we map it to a number, how many numbers can we map to? In our examples yesterday, we had 8 levels or 8 code numbers, and another one with 16 levels or 16 code numbers. What's good to give good quality reproduction of the music? It turns out for the sampling rate, there's a theorem. The theorem tells us that if you sample at a rate which is twice the highest frequency component, you'll get perfect reproduction of the audio. It's one of our this slide, the sampling theorem. It says if you sample, you have a signal, an input, our music, for example, some signal. Remember, our signals have different frequency components. They're made up of, if we look at sinusoids of different frequencies. Music, it ranges from 100 hertz up to 20,000 hertz. If we sample that at a rate which is higher than twice the highest signal frequency, in music the highest is, say, 20,000. If we sample at a rate 2 times 20,000, then the reproduction, that is the sample data and the eventual reproduction, the samples contain all the information of the original signal, and when we play it back, we'll get the perfect reproduction of the original signal. That's in theory. The sampling theorem tells us what's the best or what's the optimal sampling rate, the number of samples per second, for a particular input. If we know the spectrum of the input, we know the spectrum of music, and if we know the maximum frequency component, then the sampling theorem tells us to sample at twice the maximum frequency component. 40,000 hertz, or 40,000 samples per second in this case. For voice, and the example here, your voice has a smaller bandwidth. Typically, voice ranges up to about 4,000 hertz. So the sampling rate needed for voice should be 8,000 samples per second, twice the maximum frequency component. That's what the sampling theorem tells us. If we sample at a lower rate than 2 times the highest frequency component, if we sample at a lower rate, we'll get poorer quality. If we sample at a higher rate, we will not improve the quality. The sampling theorem tells us, in theory, the optimal rate is 2 times the maximum frequency component. So for my music, if the maximum frequency component is 20,000 hertz, if I have a sampling rate of 20,000 samples per second, or simply 20,000 hertz, versus another one of 40,000 and another one of 60,000, which one's going to give the best quality? Or easier, which one will give the worst quality? 3 different sampling rates, here's my music, which one will give the worst quality? 20,000. The lower the sampling rate, the lower the quality. This will be the worst. Which one should I use out of the other 2? 40 is 2 times the highest frequency component. If we go higher, we do not improve the quality. So this is sufficient. That's what the sampling theorem tells us. There's no need to sample higher than 40,000 hertz. We can sample at 60,000 hertz and we'll still get good quality, but we know that if we increase the sampling rate, we also increase the required data rate. So if we sample too much, we have to store more data and send more data. So in this case, in theory, we should use 40,000 hertz. This is too low, gives us poor quality. They give us the same quality, therefore choose the lower one. In practice, it's a little bit different because not only does the quality depend upon the sampling rate, but also the code numbers. So we need to consider that as well. When they record audio for the CD, because audio or the music has maximum frequencies of around 20,000 hertz, the sampling rate they use is around 40,000 hertz. It's a little bit more, in fact. This PCM with a sampling rate of 44,100 hertz. That's exactly what's used for audio CDs. Okay. Right, maybe it's slightly higher than 20,000 here. Maybe if it's 22,000, then this would be double. Okay. So with recording music to a CD, PCM is used. Sampling rate of 44,100 hertz. The number of code numbers, the number of levels, also impacts upon quality. And there's no theorem to tell us what is the best number of levels. From practice, people have determined and does measurements. Okay, if you increase the number of levels, you get better quality. Turns out with audio CDs, they use a 16-bit code number. That is about 32,000 levels, 2 to the power of 16. So remember, when we sample, we take the nearest level and map it to now a 16-bit number. And that's the data, the digital data that's stored. So with your audio CD, PCM is used 44,100 times every second. The sampler records the magnitude of the music, maps it to one of the 32,000 levels, and the output is a 16-bit number. With audio CDs, they're in stereo. What does that mean? We're just going through an example of PCM in use. What does stereo mean? Yeah, what does it mean? When someone tells you something is in stereo, what does that mean?
I don't know.
Surround, well, not quite surround sound. What else? Anyone? What does mono mean?
One.
What does stereo mean?
Two. Many.
Two channels, left and right. So with the audio, when you play it back, in fact, there's audio on the left, say the left speaker and the right speaker, and they may be different. So that's what stereo means. Mono, that you may usually hear on AM radio, there's just one channel, so the left and right are combined, you just hear one stream. Stereo means there are two audio streams. So in fact, when they record the music, two copies are recorded, the left channel and the right channel. So when you play it back, if you've got stereo speakers, what you hear in your left ear and your right ear may be different, and that creates the effect that's desired. So with stereo, we in fact store two copies of the music, two slightly different in some cases. So my question is, how many minutes of music can you store on your 700 megabyte CD? Let's calculate it. I take 44,000 samples per second, 44,100 samples every second. Every sample corresponds to 16 bits. So in 1 second, the number of bits I need is 44,100 times 16. That's the number of bits in 1 second. 44,100 samples, each sample 16 bits. But in fact, because it's stereo, I need to do that twice. I need to record both the left channel and the right channel. So there's 2 times as many bits. That's the number of bits stored every second. Let's calculate the value. I need a calculator. I have a calculator, BC, very simple. 44,100 times 16 bits times 2 for stereo, 1,411,200. And that's bits. That's the number of bits I need to store per second. Let's convert it to bytes. Divide by 8. So every second, if I sample the music, I need to store, what is it, 176,400 bytes. So when I'm recording the music, every second I store 176,400 bytes to represent that music in the digital form. I have 700 megabytes, 700 million bytes available. So how many seconds can I store? If I have 700 million bytes, in total, 1 second takes up 176,000. Total of 700 million divided by the number of bytes per 1 second means that if I store my music, I can store 3,968 seconds of music. 3,968 seconds, convert to minutes, is about 66 minutes. Approximately 66 minutes of audio. When we use PCM with these characteristics, we can record about 66 minutes of music onto a 700 megabyte CD. And you can check that if you've got an audio CD at home and see exactly how long the music, or the longest that the music lasts for. And I think it's maybe closer to 70 minutes because it's larger than 700 megabytes. So all I've done is shown an example of, well, music CDs use PCM. They take the analog data, the music, which contains a number of frequency components, and they sample it at 44,100 times per second. Each sample generates a 16-bit value, and with music CDs they do it in stereo, which means they do it twice, left and right channel. So with a 700 megabyte CD, we could store about 66 minutes of music on it. How could I store more music on my CD? I've only got a 700 megabyte CD, that's all it fits. How could I put more music on it? Okay, vary these three. Less samples. If this goes down, this value will go down and the number of minutes will go up. Reduce the sample rate and you can store more in the same space. Reduce the number of levels. Instead of using 16 bits, use 14 bits or 8 bits. Don't use stereo, use mono. Okay? Don't have stereo audio, but have just mono, so it's just one channel being played back. Which is better quality, mono or stereo? Stereo. Same. If you reduce this down to 22,000, you'll increase the number of minutes, you'll double it, but the quality of the playback will go down. Okay? Decrease the sampling rate, quality will go down. Decrease the stereo to mono, quality will go down. Decrease the number of bits, quality will go down. But we can store more music. So that's the trade-off between these values in a coding scheme. What's another way you can store music on a CD? More music. You said you had 200 songs. You said you had 200 songs on your CD. Why? How can you have 200 songs? We said we can only have 66 minutes. MP3. Use a different codec. PCM is one codec. MP3 is a different codec. It uses different parameters here. And importantly, MP3 does compression. It sacrifices quality to reduce the size. Okay? So there's again another trade-off of MP3. You get smaller size songs, therefore more minutes of music, but they are lower quality. They use a different algorithm than PCM, a different codec, and different parameters, and MP3 compresses the data. We're not going to talk about compression and how it works. You may get to study that if you choose the ICT option for your options for next semester. We'll study that in ITS323. So, importantly, we have the sampling theorem. Sample at twice the highest frequency component. You don't have to, but if you do, that's normally considered the best sampling rate. If you do less, you'll get lower quality. That was an example with music. With voice, the highest frequency component is around 4,000 hertz. So a typical sampling rate for voice is 8,000 samples per second. How many levels needed for voice? With music, we said 16-bit audio. With voice, normally it's considered about 7 bits is enough. Voice, when we play it back, like someone talking on the phone, we don't need as much quality as audio. When you want to hear someone talking, it's different from listening to music. With music, you expect higher quality, so you can use less bits to represent the voice. That's PCM and how to convert analog data to digital data. We've got one more technique to look at, but any questions on PCM? Analog to digital conversion. What are some formats of audio files that you save? MP3, other formats? Anyone else use something other than an MP3? Or seen files other than an MP3 for audio? Anything? Music or any audio files on your computer? MP3 is one format. Any others? WMA, so there's this Windows Media Audio, WMA. They're different codecs, different parameters, so they apply different algorithms for converting the analog to digital data. You may have heard of, I think Apple has a lossless codec, ALAC. FLAC is another lossless codec, FLAC. MP4 includes some audio. AC3 or AAC, audio for movies. WAV, WAV files, use PCM. So if you use your computer and record something in WAV format, it doesn't compress anything. It normally uses these parameters by default. You record 1 minute of music or 1 minute of audio in WAV format, normally it will use a sampling rate of 44,100 hertz and these parameters. So you can predict how long you can record given a particular space of memory. Different codecs in use, you apply different compression and different algorithms. Yeah? PCM is a codec, yes. It gets a bit confusing because we can say MP3 is a codec, but MP3 is also a file format and it also applies compression. So some codecs have compression, some don't. PCM does not have compression, MP3 does have it. So it gets confusing if you look at the details of some of those codecs. But yes, PCM is a codec here. The last few slides here are just some more details of how PCM can be improved or some alternatives. We're not going to go through them. Delta modulation is another approach, an alternative to PCM. We can convert digital data to signals. We can now convert analog data to digital data and transmit as some signal using PCM, for example. Last one, analog data to analog signals. We have a radio station and they have a tower on the top of their building. They're playing music. So a radio station, they have a transmit tower, they're playing music, which is of course our analog input. And you have your car with your antenna on it, and you want to listen to radio in your car, okay? FM or AM radio. So here's the radio station, they transmit from some tower a signal, and your antenna on the car picks up that signal and you listen to the music being played. In this case, our signal is an analog signal. And the music, the input, is analog data. We're wanting to send analog data as an analog signal. What's the spectrum of the music? What's the minimum frequency of music? What's the minimum of music? Our frequency components range from several hundred hertz up to several tens of thousands, around 20,000 hertz. So the music, the input analog data, if we draw a picture as a function of frequency, we plot the spectrum, then it has components of from around 100 hertz, maybe a bit more, up to about 20 kilohertz, 20,000 hertz. So there are components in this range for our music. That's the input analog data. What we want to do is transmit that across from our radio station to the car. What frequency do we use for a radio station? Can you give me an example frequency used by a radio station, maybe an FM radio station? Anyone have a favourite FM radio station? FM radio? 107. 107 what? 107.0 what? Megahertz. 107.0 megahertz. That is so that's a radio channel that you listen to, or particularly that's the center frequency for that particular radio channel. So how we could draw that is think that we have a signal and just a sine wave, and the frequency is 107.0 megahertz. just a simple sine wave. In fact, okay, we'll see in a moment. We want to send a signal at that frequency from our radio station to the car, but that signal needs to carry some music. If we just send a sine wave, it will not carry the music. We need to vary that signal such that the receiver will be able to receive and play back the music. So what we do, this is using FM radio, we change the frequency of this signal according to the magnitude of the music. So if we plot a picture of the music as a function of time, then we're going up and down. It depends on the music. Okay, so that's our input data. What we do is that we take our signal, our sine wave with a frequency of 107 megahertz, and vary the frequency of that, so plus or minus some values, depending upon the input data. I will not try and draw it because it's hard, but we've got an example in a moment. This is the one I've drawn on the board. Say this is a frequency of 107 megahertz. And then we have our music. Okay, the music's varying over time. That's, in this slide, the middle diagram is our music. All right, in this case, it's a very simple form of music, so it's a simple sine wave, so that we can see it. What we do to transmit a signal is we take our input, what's called a carrier signal. This is the carrier signal. We take our music, the input data, and we vary the frequency of the carrier according to the magnitude of the input data. And the output in this example is what's shown at the bottom. We can see as the data has a high amplitude, the frequency is larger. As the data has a lower amplitude, the frequency is higher. See, we take this as a starting point and vary the frequency. We make it larger, and we make the frequency lower. It's less frequent here. And when the signal is low, we have increased the frequency of our carrier. And this is the signal that's transmitted. That's this signal here. It's centered around 107.0 megahertz, but it's varying slightly. So it's a little bit less than 107 and a little bit more than 107. And those variations depend upon the music or the input analog that's being transferred. So that's the concept of frequency modulation. FM radio, frequency modulation. We have a carrier signal at some frequency. We have some input data which modulates the carrier, such that is, it changes the frequency of the carrier according to the input data. And this is the transmitted signal that comes out and is sent to your car, and the car antenna receives that and looks at the frequency here. When it's a low frequency, it knows it's a high magnitude for the audio, and when it's a high frequency, it knows it's a low magnitude here, and generates that audio output again and plays it back on your speakers. So that's an example of how we can send our analog data, the music, as an analog signal. In this case, we varied the frequency of a carrier, frequency modulation. There are other ways that we can vary it. We can vary the phase of the carrier, phase modulation, PM. Same approach, carrier, data, change the phase according to the input data. It in fact looks like frequency modulation. You look at this and compare it to this one, of course it's changing the frequency but at different locations. The other one, amplitude modulation. Take the carrier, here's our input data, and change the amplitude of the carrier according to the input data. We see here, we can see the amplitude of the carrier is following the amplitude of the input data. When it's negative here, we've got a low amplitude. When it's positive, we've got a high amplitude. So this would be the transmitted signal if we were using AM radio. Our music, our carrier frequency, and the transmitted AM radio signal. Change either the amplitude, the phase, or the frequency of the carrier signal. Similar to our shift keying, but remember shift keying was about sending our digital data as analog signals. This is about sending analog data as analog signals. In shift keying, we had amplitude, phase, and frequency shift keying. In modulation, we have amplitude, phase, and frequency modulation. Any questions on how they work? They're the main concepts that we want to cover for those three techniques. So now you know how your AM and FM radio works in your car. Importantly, if we draw this signal, this is in the time domain. In the frequency domain, I'll make it a bit bigger. Here's the frequency of 107.0 megahertz. And because the frequency, in fact, varies a bit, we could say it's normally this is the bandwidth. The bandwidth for FM radio, I think, from memory, is around 20 kilohertz. That is, the signal that we transmit is not exactly at one frequency, it's a range of frequencies. Centred around 107.0 megahertz with a bandwidth of about 20 kilohertz. With a bandwidth of 20 kilohertz, we can transmit our music at good quality. With AM radio, we use a lower bandwidth.
Is this frequency domain?
This is a plot in the frequency domain, yes. So this is whatever 107.0 minus 10 kilohertz is, this value here.
What is that axis?
This is the peak amplitude. If you remember back to our signal lecture on signals, we had a signal in the time domain, as shown here, and here in the frequency domain. In the examples we used, we had impulses, but in practice, it's a continuous range of frequencies. It's not just 1, 2, 3 components. There's a range of components, so we normally draw it as a continuous line. What it's really saying is that the signal that we transmit has a bandwidth of about 20 kilohertz, centered on 107.0 megahertz. Can you listen? Are there other radio channels?
Yes.
What's another one? Other FM channels?
102.
That's it. 102.5. All right. Another channel. So there's another radio station somewhere. They transmit their signal, their music. They're using a different centre frequency, say 102.5 megahertz. Same bandwidth signal, but at a different frequency. And they're transmitted at the same time. So there's two radio stations, 2 towers transmitting the signal. All you do on your car is change the channel or the frequency you tune into. So both are being transmitted. Effectively, you're receiving both signals, but the antenna with the tuner only picks up on a particular range of frequencies. So you tune into 107.0 and you receive and play back this signal. If you tune into 102.5, you'll get this signal. These centre frequencies are allocated to companies who own the radio station through some licensing scheme. So a company says, I want to start a radio station, FM radio. You need to get a license to use that frequency and that bandwidth, because they must be separated such that they don't interfere with each other. We cannot have another one here, because your car would receive both of them and they would interfere, and your car, you would not be able to play back the music. So the licensing is arranged such that there are certain channels spaced far enough apart in the frequency domain so that they don't interfere with each other. And that's why it costs money to get a license, because we only have a certain portion of the spectrum available. There's competition. Many people want a license because they make money from adverts and so on. So it costs money. You need to pay some license fee, some tens of millions of baht or whatever, to use the license every year. And you must transmit within some bandwidth. If the station transmits a larger bandwidth signal, that it will be outside the rules of the license, and they may get penalties or financial fines for doing so, because otherwise they'd interfere with other stations. Now that's an example of FM radio, AM, same concepts. Any questions on how do we send using AM, PM or FM? The other slides, I think, just summarise or give another example of what we're trying to show there. You may see some questions in the past exams or quizzes along the lines of describe, or here's a description of FM, describe AM, amplitude modulation. Well, how do you describe it? With amplitude modulation, we change the amplitude of our carrier signal according to the input data. With frequency modulation, we change the frequency of the carrier signal according to the input data. We've gone through some of them quite fast, but I think you should be able to distinguish between the different techniques and at least know where they are applied. Let's move on to the next topic. We're going to move up from the physical layer to the data link layer. Everything that we've spoken about until now is about how do we send data as some signal. Different types of data, different types of signals. We can think of that as the physical layer, sending data as signals. The data link layer is how to make sure that data arrives correctly at the destination, at the other endpoint of the link. We're going to focus now on the data link layer. And from now on, we're going to use in most of our examples digital data. What we're sending is bits. Okay? To keep things simple, we'll focus on digital data. This topic we're going to skip, except for a very short explanation. The concept that this topic was supposed to cover, and we're not going to cover in detail because we don't have the time, is that when we send bits, we may get bit errors. Let's draw an example of a bit error. Let's say my device transmits a sequence of bits. Let's say 8 bits, just a random sequence of 8 bits. And we transmit that set of 8 bits. We send it across a link. We send it as a signal. There may be some noise in the system, some interference. Remember, what we receive may not be the same as what we transmit because of the noise and other transmission impairments. For example, the receiver receives a signal and decodes it and thinks that the bits transmitted were were this, then we have a bit error. These are the sequence of 8 bits, 0, 1, 1, 0, 1, 1, 1, 0. This bit here is an error. Okay, that's a bit error. We can get bit errors if our transmission link is not perfect. Okay, that can always happen. We don't want errors, but they may occur. We cannot stop them in some cases. What we want to do, if there are errors, is to detect them. That is, the receiver wants to know that there is an error, and if we can detect it, we can potentially correct the error, fix it. Error detection and error correction are two important principles or techniques used in the data link layer. If there is an error, somehow the receiver needs to know that there is an error. It doesn't know what was transmitted. It's on the other side of the link. It only knows what is received. How could the receiver detect that there's an error in this sequence? It doesn't know what was actually transmitted, because if it did, it wouldn't be a problem. How does it know that there's an error there? Well, there are different algorithms. The concept is that you send some other bits. You send some extra information here, such that when with that extra information, the receiver can check, is this sequence of 8 bits correct or not? Are there any errors? And you probably have heard of parity checks when you look at computer hardware. Parity checks are applied to check whether the data has an error or not. Same concept. We send some parity bits, some extra bits, as well as the data. So this is the data, plus some extra bits, such that when the receiver receives all those bits, they can use those parity bits to check whether there's an error there or not. So parity check is one algorithm for error detection. Another one you may have seen or heard of is a CRC, cyclic redundancy code check, CRC32 or CRC16. They're different algorithms. Again, we send the data plus some extra bits, such that when the receiver receives all of them, it can compare the data with what's in the extra bits. If something doesn't match, it detects an error. These are error detection algorithms or error detection schemes, Parity, CRC, and there are others.
So it's like the duplication of the original.
All right, let's give a quick example for parity. One simple, it's not duplication of the original. Here's our data. A parity check, one parity check is add a bit such that the number of ones is even. Okay, here we have 8 bits. Add one bit such that the number of ones in total is even. What do I add here?
1.
All right, I currently have 1, 2, 3, 4, 5 ones. So if I want of all 9 bits, the total number of ones to be even, I add a parity bit. This is my parity bit, which is the value 1, such that now I have 1, 2, 3, 4, 5, 6 ones. I have an even number of ones. Now, we transmit those 9 bits. If the receiver receives those 9 bits, so it receives those 9 bits, what the receiver does is counts the number of ones. How many? 1, 2, 3, 4, 5. It expected an even number of ones, because what the transmitter did was made sure that there was an even number of ones when it sent. If there were 5 here, it added a 1. If there were an even number already, it would add a 0. Yeah. So the transmitter makes sure whatever is transmitted, there is an even number of ones, always. So now the receiver receives a sequence. If there are an even number of ones, it assumes no error. If there are an odd number of ones, as in this case, it assumes there's an error. An error has been detected. So there's a very simple case of an error detection scheme. because here we have 5 ones, because we know that this one changed from a 1 to a 0. If one bit changes with 1 bit error, if we start with an even number of ones, if there's 1 bit error, we'll end up with an odd number of ones. An even number plus or minus 1 will be an odd number. So that's an example of the simplest, or one of the simpler error detection schemes. The receiver doesn't know which bit is in error, it just knows that there is an error somewhere. Understand? Parity check. The transmitter makes sure, in this case, it makes sure that there are an even number of ones. 8 bits of data plus 1 parity bit. There are 6 ones, an even number of ones. When we receive it, there should be 6 ones, or an even number of ones. If nothing goes wrong, there will be an even number of ones. If 1 bit is in error, there will be an odd number of ones, and we detect that error. So we perform error detection. There are other error detection schemes. This is just one simple example. There should always be an even number of ones transmitted. If there are an even number of ones received, no error detected. If there are an odd number of ones received, error detected. Any questions on how that works? We're not supposed to cover that, but just to give an example. There are more complex algorithms such that we take our data, we add some extra bits, and the receiver can use those extra bits to help it detect if there's an error or not. That is, perform error detection. That's common in most of our transmissions. We add some extra bits to help us detect errors. Yeah? The extra bit helps us because, okay, another case. What if the original data was this? The original data was this sequence of bits. What do we add here? We've currently got 6 ones. The scheme is always transmit an even number of ones. So we add a bit 0 here. This extra bit is just making sure that we always have an even number of ones that is transmitted. If we have an odd number in the data, we add a 1. If we have an even number in the data, we add a 0. So it's just making sure the total number of ones is even. And therefore, the receiver must expect an even number of ones. If it receives an odd number of ones, there's an error detected. It's not so much about where the error, it's just that there is an error. There are other algorithms. What do we do when we detect an error? What do we do when we detect an error? When you find an error in your exam, what are you going to do? In their marking for your exam, you find an error. I've added up wrong. What are you going to do? What will you do? You see your exam and you see that I gave you 40 out of 90 and in fact you should get 50 out of 90. What do? You tell me. And what do you expect me to do? to change it, to correct it. We want to correct the errors. It's no good just to detect errors. Error detection is needed, but once we detect errors, what do? We should correct them somehow. How could we correct this error? One option, ask the transmitter to resend the data. Say the receiver says, I just received some data, there is an error in it, please send again. And we'll hope next time that it will not have an error, there will be no noise or whatever caused the error. That's one approach. Our next topic covers that. Another approach, and it's called forward error correction. Another approach, and that's what this topic covers, similar to error detection, transmit a different sequence of bits that represents this, apply some algorithm on our input data, transmit a different longer sequence of bits, such that if there's an error at the receiver can use that extra sequence of bits to correct the error. It can correct the error even without asking for a resend, because we send some extra information with us. So not just the data, but include either some transformation or some extra information so that the receiver can detect and correct the data, the error, sorry. That's possible. We're going to focus on this one, which is the more common one. I send some data, you detect an error, you ask me to send again. That's what we'll cover. Retransmission schemes. So we just finished that topic. So we can start our next topic. I'm not going to ask you how parity checks work, but understand that we can have a... It's nice to understand. You can check those notes. You ask a question, yeah.
Do the transmit parity bit is 0, do the receive have to be 0 also?
This is a different, yes. But there could be a bit error here. It may not be, okay? If there's a bit error, then we could detect that. This parity check will detect 1-bit errors, more generally an odd number of bit errors, but if there were 2 bits in error, it wouldn't work. This parity check scheme wouldn't work if we had 2 bits in error. You can check and confirm that. It only works some of the times. It only detects some errors. That's the problem with error detection. It's not perfect. Yeah. 1-bit errors are detected, 2-bit errors are not detected. And in fact, even bit errors are not detected in this simple scheme. So there are more complex schemes which improve the chance of detecting errors. For now, I think we assume the receiver can detect errors. In most of the cases, it can detect errors. We want to focus more on how do we ask them to resend to correct those errors, which is a feature of data link control protocols. The physical layer is about getting our bits from A to B. The data link layer and the protocols in the data link layer control that link, including making sure the bits are delivered reliably. Today we'll just introduce this so that next week we can go into the details. Physical layer, sending signals representing our data across a link. More things are needed to get our link to work. We now talk about sending not just data, but a block of data. Here I had a block of 8 bits which was sent, plus a parity bit. This block of data we'll commonly call a frame of data. So in fact, altogether, this is a frame. So now we don't just deal with a sequence of bits, we break those bits into blocks where each one is a frame. Normally the frame contains some data and some header or trailer information. This may be part of the trailer, for example, the thing at the end of the data. So we sometimes draw a frame like this rectangle where we have data, a header, and at the end, if we have something at the end, the trailer. That's the general format of the frame, where the trailer may contain information such as parity bits or other error detection information. The header contains information necessary for the protocol to work. One thing included in the header commonly is some address. Who are we sending the data to? When you send an email, you specify a destination address, the to address. So the network will deliver it to the correct destination. Same in the data link layer. When we send our data frame, we'll normally include in the header the destination address. So the link knows who to deliver that to. Not just the destination address, we'll also send the source address. Who did it come from? So that the destination knows who to send a response to. If I send a message to someone, often they want to send something back to me. So if I include my address in here and their address will tell the link to get it to the right person, and my address will tell that person who they can reply to if they want to reply. And other things are included in the header. But the structure of the header, the structure of the addresses is normally part of the data link layer. So the data link layer has to define the types of addresses. We saw at the start of the course some example addresses for our wireless LAN or Ethernet cards. A quick example. On my computer, we can see the hardware address. That's an example of a data link layer address for my, in this case, my wireless LAN card. So that's part of the data link layer, creating the address, assigning the address. And other features. When we create a link, anyone have an ADSL modem at home or in their dorm? Anyone? Anyone seen an ADSL modem? Yeah? And when you plug it in and turn on the power, remember it's connected to the cable that goes into the telephone line. You turn on the power and some lights flash, because before you can send data, it's establishing the link to the other endpoint. It goes through some procedure to create this link, to establish and maintain a link from your modem to the telephone exchange. Those features are part of the data link layer. Link management, controlling the data, and controlling the link. So there are different protocols for doing that. Data link layer often includes error control, like we said. We send some data in a frame. If the receiver detects an error, ask the transmitter to resend. Please send it again. Please send it again. Okay? That's error control. And the last thing, and the first thing we'll cover next week, is flow control. Quite simply, in the lecture, if I'm talking too fast, you will not be able to take anything in. Okay? If I cover the topics too fast, which I think we do sometimes, then you will not be able to understand it all. What do you do in that case if the lecture is too fast? Ask me to slow down, because what's happening is I'm transmitting the information to you too fast and it's overflowing your brain. Okay? You've only got a certain amount of memory in your brain to store things. It overflows and many things don't go into your brain. So what you should do is ask the transmitter to slow down. The same happens in networks. We have flow control. The device is sending data to a receiver. The receiver has a certain amount of memory to store the data it receives. If it arrives too fast, the memory will overflow. And the receiver will tell the transmitter, please slow down, you're sending too fast. We will look next week at different protocols for doing flow control and error control. The other parts of data link layer we're not going to look at, just flow and error control. But that will be next week. We'll spend some time on flow control and error control next week. Any questions on what we've covered today?